Hi, I'm Scott Vaughn. In this video, I would like to present some work I did with a former student of mine, Alexis Androlonis. Alexis was my student in spring 2024 when she did an independent study course on mathematical modeling and scientific computing. In this video, we look at the math, physics, and programming behind finding solutions to the general three-body problem. We start with an overview, but quickly get into the details of the engine behind finding and plotting those solutions. Okay, so the topics in this video are an overview of the Runge-Kutta fourth order numerical integration method. We use that to look at solving the three-body problem using RK4 in Python. And then we look at validating the solutions that we generate in Python. So the fourth order Runge-Kutta method, or RK4, it's a common method for numerical integration. So numerical integration is required in this case because there is no closed form exact formula or analytic solution for the three-body problem. And RK4, it balances accuracy with speed. It's more accurate than Euler's method, but it's faster than higher order methods. The RK4 method, it matches the accuracy of the fourth order Taylor series approximation to the exact solution, but it doesn't require higher order derivatives. And the local error, which is the error at each individual time step, it's proportional to h to the fifth, where h is the step size. Another way of saying that is that the largest term in the local error is some term of the form a times h to the fifth, where a is some constant. So it was the goals of this project, this work that I did with Alexis, to develop a custom implementation of RK4 in Python to solve the three-body problem. And we did that to develop our coding skills and our understanding of RK4. But, the three-body problem is chaotic in general. So how do we know that our code is even correct? Well, there's a couple of ways to approach that question. We can start with initial conditions for known stable configurations, such as the figure 8, and I'll demonstrate that. We can compare the results with the built-in numerical integration methods that are already available in Python. Both Alexis and I, we independently wrote our own implementations of RK4, and we compared the results that we got. That was another way of validating our solutions. And finally, we could compute the mechanical energy and center of mass in the three-body simulation and compare the results we get in the simulation with what we would expect from the physics. So a quick overview of the RK4 method. We're given, in general, a first-order differential equation with some initial conditions and some unknown exact solution. You can just barely make out the exact solution in red in this graph. And we're looking for a good approximation to that unknown exact solution. So the approach in the numerical method would be to evaluate the differential equation at incremental time steps, finding the direction of the solution at each of those time steps. Now, Euler's method estimates the direction of the exact solution from the differential equation once at every time step. And RK4, that method, averages multiple estimates of the direction of the exact solution using the start and midpoint and endpoint of each time step. So stepping back for a moment and thinking about a numerical approximation to finding an exact solution, let's begin with, let's say that we're looking for an exact solution to a differential equation. The exact solution, it's shown here as this blue curve. And if we could identify the slope of that unknown solution at a specific point, let's say x1, y1, that could be our initial condition, or at any point along our approximation. At any point, we have a point that we think is on the curve and pointed in the direction of the curve. We can identify that slope, right? So if we think about what's the equation of a line in general, that's what I have here, the equation of a line. And if I'm looking for another point on the exact solution, I could use that equation of the line to find that second point. Here I'm calling it x2, y2. And of course I want to make the step sizes small. And so then I could actually identify what would that y2 point actually be by just solving for it. I'm going to add y1 to the other side of the equation here, and now I have an expression that identifies that second point. When I plug in x2, I can find the second y value based on the tangent line there. Well, of course, if I have a derivative for the solution, here I have it written as f prime at x1. That's the slope of the tangent at x1. And of course, I'll multiply that by h, where h is the step size, and then add to the previous y value, in this case y1, and it gives me y2. So that's sort of how you could get that next point using the slope of the tangent by using the derivative, if we have the derivative for the unknown solution. But of course, that's what you have when you're differential equations. What I've just described is essentially what Euler's method is. In the differential equations class, we probably wouldn't write f prime at xn. We would write f at xy, where we have from the differential equation, because it's a differential equation, of course we have the slope at any point if we just plug in the x and y. So that just extends now to what's the RK4 method. Instead of just getting the slope at one single point, we're going to get a whole bunch of slopes using the beginning and end and midpoint, and counting the two in the middle, the two estimates in the middle twice. So that's the reason why we're dividing by 6. If you kind of look at sort of 6 values, right, 1, 2, 3, 4, 5, 6, when you add all these together, I'm dividing by 6 to get a weighted average, where I weigh the middle two values, the K2 and the K3, heavier in that calculation. So it really is ultimately the same thing as finding another point on the tangent line. It's just we're getting a lot more sophisticated in how we get the slope of the tangent. We're using a weighted average of several estimates of the slope. We take that slope, multiply it by the step size, add to the previous y value to get the next y value. This just dives a little deeper into a visualization of how that actually happens. So in differential equations, we begin with a first order initial value problem. That is a differential equation that's a first derivative. Here, f represents the formula that you have in the differential equation. Here, my independent variable is t, my dependent variable is y, and I need some initial condition. Here, it's y at t0 equal to y at 0. So, and of course, once again, we have an unknown exact solution that we'll call y of t. That's once again shown here in blue, and we'll refer to h as the step size. Then we calculate these slopes that we call k1, 2, k3, k4. And then we estimate our new point that's hopefully very close to the exact solution, which is here in green. This t1, y1 is our final estimate of the new point based on the slopes k1 through k4. Let me just talk quickly through kind of like what's really going on, because the picture's pretty complicated, a little overwhelming. So imagine, let's say in the picture that we have here, we're starting at the initial condition, t0, y0. We're at that point, and then we take that t0, y0 and just plug it into our differential equation, and it tells us the slope at that point. And that's the slope here at t0. And that slope, we call that k1. And then we say, all right, if we follow the direction of the solution with k1 and you go a half a step, you'll be about here, right? This would half step forward using that k1 slope, but only half of a step. So we multiply half a step times k1 to get the y0, to get the next y value, right? So added to y0, half a step times k1. That gets me at that point. That's an approximation for where the solution should be. Then once again, I'll plug that into the differential equation and get a new slope, k2. So that's the slope evaluated from the differential equation, what the differential equation implies the direction of the solution should be, and that's what we call k2. Once you have k2, then we're going to go back to the beginning of the interval and use the slope that we just calculated, k2, and propagate forward a half a step. And that would put us here, using k2 times a half a step added to the previous y value to get this point a half step forward. At that point, we once again calculate another slope using the differential equation, and we call that k3. So k3 now, we go back to the beginning of the interval and use the slope k3 and propagate forward a full step based on the slope k3, which gives us this point right there, presumably very close to the exact solution, but maybe still not right exactly on it in general. So then once we're at that point, then we will once again use the differential equation to find a slope. What does the differential equation imply that the slope of the exact solution would be at that point? And then once we have K4, now we go back to the beginning and we use an average of all of those slopes, K1, K2, K3, and K4, and we get that new point T1, Y1 that's computed using an average of the slopes K1, K2, K3, and K4, and this time with a full step. So here that's written a little more formulaic, a little more precise in terms of the notation. So once again, I'm given an initial value problem. The goal is to estimate y of t over some given interval that's divided into steps of size h. We've got a differential equation and initial condition. We propagate forward to get y sub n plus 1 based on the previous yn value. And we add to that a step size times an average of those k1, k2, k3, and k4 values, where we have a weighted average counting the middle two twice. And there it is written out a little more precisely that K1 is from the differential equation at the t and yn in general. Here it was just using that point t0, y0, but now you can see I'm building a kind of recursive formula so that I could each time calculate these k's, K1 being the point at t and yn, but then K2, I'll just take a half step forward and use the K1 slope. So there's the recursion, right? I'm calculating K2 using the slope from K1. And then I'm calculating K3 using the slope from K2. And then I'm calculating K4 using the slope from K3. And then I'm using all of those slopes to get the next point from yn. So now I'm ready to go back to the three-body problem and just build up quickly the equations that we're going to try to solve. So of course, Newton's law of gravity is the force is the product of the two masses times the universal gravitational constant divided by the distance between the masses squared. And that's how we describe gravity between two objects at a time, right? And so I could say that, well, let's say for the acceleration of body 1, that force is mass 1 times acceleration 1. And I'll divide out the mass 1 so that I can actually describe acceleration of body 1 as this number here. So this is the acceleration of body 1, but it's just a number. And in the three-body problem, I need to keep track of all these relative positions to calculate accelerations, to plot trajectories. So I need to describe the acceleration as a vector. So there is the magnitude of the acceleration due to gravity that body 1 experiences. And here I'm dividing by a unit vector so that only the magnitude of the acceleration is by Newton's law of gravity. And because these two factors in the denominator are the same, you can put them together and make it a cube. And another comment, the negative is there because the way I've captured the vector, I'm measuring from body 2 to body 1, but the acceleration that body 1 experiences is opposite to the vector as I've defined it, is in the opposite direction. That's why the negative's there. So the accelerations for all three masses are the sums of accelerations of each mass in the gravity field of the other two masses. And that's what's captured here. And those accelerations are second derivatives of position. So I have a system of three second-order differential equations. So there is no exact general solution as a formula for the solution for the position of these bodies over time. So that's why we go to a method like RK4 to plot out an approximation to the solutions. And that's what we'll do. So the thing with the RK4 is that it requires first-order derivatives. And so what I could do is just take each of those equations that are second-order derivatives and turn them into a pair of first-order derivatives. Because, of course, the acceleration is the first derivative of velocity. And the velocity, it's the first derivative of position. So for each of those second order derivatives of position, I'll just write them as first derivatives of velocity and position. And that's what I'll then create a system of differential equations, here written as basically 6 differential equations that I'm going to solve simultaneously with RK4. But when it comes to actually thinking about the code, I even want to break it down a little bit further. If I'm going to be in two-dimensional space, I need to keep track of the velocity of body 1 in the x and y direction and the acceleration in the x and y direction. So I kind of have 12 differential equations in a sense because I have 4 derivatives for each of the 3 bodies. So when I put this in the computer, how do I know it's even correct? So of course, there are known configurations, sets of initial conditions that should lead to a particular configuration or outcome in the trajectory. So I can put in those known initial conditions to make sure that it generates what I expect, like for example, the figure 8. And I have another one that I'll demonstrate where I have these intersecting ellipses. So that's one way of checking that I have the code right. Another thing would be this, actually Python has built in an integration method. I could just use the built-in integration from the SciPy library in Python and make sure that I'm getting the same thing in my custom RK4 that I code with the one that was built in to Python. And as I said, Alexis and I, we each wrote our own custom implementations of RK4 in Python. And so that was another way of validating that we were both correct, that we both had the same result. And finally, we'll look at computing the total energy and center of mass in the 3-body problem. And we can continually update the center of mass and the total energy in the simulation. And print those results, and we can compare with what we would expect from the physics of the situation. So let's look at this initial condition, these initial conditions first. I'll take the universal gravitational constant B1. I'll set all 3 masses of the bodies equal to 1, and then I'll enter these initial positions and initial velocities for bodies 1, 2, and 3 into the Python code. And this will generate a figure 8 if the code is right. And I'm going to just talk a little bit about how I set up the code, and then I'll show you the code I use. So can sort of think of it as these sort of 4 parts. I have the initial conditions that are set, which feeds into this thing that I'll think of as the main loop. That main loop is then calling another function that I called RK4 step. And it's that RK4 step that then calls another function that I call DSTT. So the DSTT represents like a derivative of the state vector. That state vector is capturing positions and velocities. So then when I'm in the RK4 step, I'm going to send the current positions and current velocities to the DSTT. Now, DSTT only needs to know the positions in order to calculate accelerations. But I send it positions and velocities just because I want to keep all that information together. It was handy to do it that way. I compute the accelerations based on the positions, but then I return the velocities accelerations back to RK4 step, back to that function. It receives the new updated velocities and accelerations, and then it computes new positions and new velocities stepping forward based on what my time step is, and using RK4 and the RK4 algorithm and the weighted averages of all K1, K2, K3, and K4. Once that's done, I go back to the main loop, update the state vector, plot the new positions, increment the time step, and start again. That's the outline, basically how the code works. So this is Trinket, which is a nice place to write Python code for physics simulations because it automatically has built-in functions to do the animations and to also keep the window on any objects that are being plotted. So yeah, and here I have the initial conditions for the figure 8 set in to the code here. So let's see if it's working. That looks good. There's the figure 8. Now let me just talk really quickly through the code just a little bit here. I've got the universal gravitational constant set, each of the masses set to 1. I've got some parameters that I use for time. I actually am doing a collision detection here in this code. So here's the DSDT function. I'll talk about that in a second. There's RK4 step. And there's checking for collisions just to see if the distance between two objects is less than a certain fixed value. And here's where I plot the vectors. I plot the bodies, the three, as spheres. And there's the main loop, and that's the whole entire code, right? And then I'm just updating their positions in that loop right there. So let me just back up a little bit, right? So it's the dsdt that's kind of like the derivative of the state vector. In a sense, it calculates distance between the two bodies. It then calculates the acceleration. It then gets x and y components of the accelerations for each of the three bodies. And then it returns the velocities and the accelerations. That it received the velocities and positions, and then it sends back velocities and accelerations. It sends them back to the RK4 step. RK4 step is taking the current state vector, and it's calculating what all of those slopes would be. The change is basically in the velocity by using that dsdt and calculating what the acceleration should be. And it just keeps track of all of those sort of simultaneously and updates each of those, well, computes each of those four different slopes, right? And then it uses RK4 to update all of the state vectors using that weighted average that RK4, the standard RK4 does. And then it returns the new state, which is the new state vector with all the new positions and velocities. And yeah, that's generally all there is to it, right? That's how it works. One thing that's kind of fun now is to play around with the initial conditions. So here's another really neat configuration that I think is pretty fascinating. Let's set all the masses to 1.5. So, I'll put the code for this in the link to the code in the description so you can play around with this. But here's one thing to try. I'm going to change this. I'll just call this like the intersecting ellipses. And now run the same thing. And that's just pretty neat. Now, it's kind of interesting with this that the figure 8 is very stable over a very long period of time, but it doesn't take too long for this one just to drift off a little bit from that initial trajectory. And once it drifts off, there it goes. Now it's pretty much chaotic. I don't know what's going to happen. So that's kind of fun. Now, these are the initial conditions for those three intersecting ellipses here, if you want to try this. And I'll put those same conditions into the code that was written by Alexis. So here's her code, and I have commented out the figure 8, and I have the intersecting ellipses, and her code, well, it's obviously different, and honestly, it looks a lot shorter. She's a better programmer, for sure. So let's run that. So there it goes. Now, the initial conditions that you see here at the bottom that I call sort of the Pythagorean triangle, I'll set the masses all back equal to 1 and put each body at the corners of a right triangle. Now I have each of the three masses at the vertices of a right triangle, so it's easy to calculate the center of mass and the total energy by hand, and then we can check that it is the same in the computer simulation. So in order to find that center of mass, what we could do is we need the x and y coordinates. We get that as the moment about the y-axis divided by the sum of all the masses. The moment about the y-axis is each x coordinate, each x component for each of the coordinates multiplied by the masses, each of the masses divided by the total mass, and that comes out to be 0. So now I say, okay, well, this thing is balanced about the y-axis. The center of mass is right on the y-axis. And for the the y value for the center of mass, I get the moment about the x, which is actually all of the y coordinates, all the y values, all the y components of each coordinate. So each of the y values for each of the positions of the three masses, the y value for body 1 and y value for body 2, the y value for body 3, I multiply each of those by each of the three masses, divide by the total mass, and I get the y coordinate for the center of mass. So I know the center of mass should be at 0, 1/3, should be right there, roughly in the simulation, and should stay there, according to the physics of this situation. And then also I could very quickly calculate the total energy as the sum of the potential and kinetic energies. And in the Pythagorean configuration, it's really easy to calculate each of those. In that initial, in the initial conditions in this configuration, I'll have a 0 initial velocity. So I'm placing all three bodies on the corners of a triangle with 0 initial velocity. So my kinetic energy starts off at 0. And how about the potential energy? The potential energy is a value that we measure between two masses. And so the potential energy between mass 1 and 2, I'll compute here, between mass 1 and 3, and between masses 2 and 3. And so all I really need to know, each of the masses in this configuration is 1. My gravitational constant is 1. So the numerators are easy to compute here. It's only the denominators that are the distance between them, between the masses, that I need to update. And the initial conditions, the distance between mass 1 and 2, that's the hypotenuse of this triangle. That distance is 5. The distance between mass 1 and 3, that distance is 3. And the distance here, it's 4. So the distance between mass 2 and 3 is 4. The distance between mass 1 and 3, that's 3. And the distance between mass 1 and 2, that's equal to 5. So I'm just adding all those fractions together. I know that the exact potential energy is negative 47/60. But I'll continue updating and have it print that in the simulation in decimal. So I'm looking for the total energy to stay at negative 7.83. Now, once they start moving under the influence of gravity, the kinetic energy will increase. And as this increases, I would expect that to decrease so that I could keep that value constant.
Okay, so here I am back in Trinket and set up the initial conditions for this Pythagorean triangle. Initial velocities all 0. The bodies on the corners of a right triangle. And this is the same code that I had talked through a little bit before, but now what I've added is functions to compute kinetic and potential energy, and here I calculate it at the initial state, and then here I am calculating the center of mass and calculating kinetic and potential energy and total mechanical energy as the sum of those two inside of the loop, and constantly updating it in the animation. And there I can see the center of mass, and I can see the total mechanical energy as the value that I expected.
All right, so now to just sum up a little bit here, I expect the center of mass to remain fixed in place throughout the simulation, as there are no other external forces, no forces other than the forces of gravity between each of these three bodies. And thus the center of mass of the system shouldn't move in the coordinate system. And that's what I observe. Also, for the same reason, I expect the total mechanical energy to remain fixed throughout the simulation. However, I do notice, after a few seconds, when two of the bodies get very close, there's a sudden change in total energy. I think what's happening here is that as the two bodies get very close to each other, they create very large gravitational forces on each other, increasing the accelerations, which lead to increasing velocities, which at some point is just too fast for the fixed step size I'd chosen at the outset. At that point, the simulation is basically failing. The positions are no longer updated accurately enough
as they would need to be changed more quickly than the step size allows, even using RK4. I tried the same calculations in standard Python with its built-in integrator. That method updates the step size dynamically as the simulation runs. In that case, I see the total energy actually jumping around, actually even a little bit more, and always when two bodies approach closely. I'm not exactly sure why that variation in the total energy occurs this way. I'm thinking it's a sort of indirect byproduct of some differences in the rounding in the calculations for both kinetic and potential energy that are fluctuating as the step size changes. And this brings me to the final point that I'll share in this video. There are more sophisticated integration methods than RK4, and they are really useful for animations of the general three-body problem. I've now realized probably most of the animations of the general three-body problem that we see on YouTube are generated using integration methods more sophisticated than RK4. For example, I wanted to compare the RK4 that I'd coded in Python with the built-in integrator that's called solve IVP in the SciPy library that's part of standard Python. And the default for the solve IVP method is what's called RK45, and it essentially uses a fifth-order approximation to compute some error bounds on the fourth-order approximation. If the fourth-order approximation exceeds these error bounds, the RK45 method dynamically adjusts that step size to get a more accurate plot of the positions in the general three-body problem. It's better to use an integration method with an adaptive step size like solve IVP in standard Python. So to generate an animated plot of trajectories in the general three-body problem using an advanced integration method with an adaptive step size, this is computationally intensive. It took my computer about 3 days to generate this animation here using standard Python with the code written in PyCharm. First, here we see the plot using solve IVP, the more accurate integrator that has the adaptive step size. And then following that, we see a plot of the trajectories of the three bodies based only on the classic RK4 integration with a fixed step size, what I called my custom RK4 implementation, as I'd written and demonstrated in the Python code that I had on Trinket. So these are very closely aligned initially, at least, up until that moment when the two bodies approach each other very closely. Then the RK4 diverges from that more accurate solution that was plotted with solve IVP. Okay, so that's the end of the video. I hope you enjoyed it. Thank you very much for watching.